This is a video showing initiation of depolarization in a neuron, the ions and gradients that are involved, as well as the active and passive channels that are present. The action potential refers to the brief change in membrane potential due to voltage-gated ion channels. This allows neurons to transmit electrical signals between one another. Prior to the action potential, the cell is at resting membrane potential, or about negative 65 millivolts. There are certain triggers for the initial sodium influx of an action potential, such as activation of chemical or stretch receptors, as well as changes in temperature or light. Since chemical receptors are a little bit more easy to conceptualize, that is what we will use in this video. So in a neuron, let's say there are chemical receptors that are embedded within the membrane of the soma, and some sort of ligand binds to the chemical receptors and causes its conformation to change such that it opens and allows sodium inside. So once this occurs, sodium starts to enter the cell, and because all of these positive charges are coming inside, it causes the membrane potential to rise ever so slightly until we reach negative 55 millivolts at the axon hillock, also known as the trigger zone. At this location, there are several voltage-gated sodium channels. So once all of this sodium starts to come in and follow its concentration gradient, these voltage-gated sodium channels all of a sudden become activated and allow sodium to come inside. From our last video, we talked about how the inside of the cell tends to be a little bit more negative due to organic anions that are present. So sodium not only is chemically motivated to come in due to its abundance in the extracellular matrix, but it is also electrically motivated to come in as well. So once these voltage-gated sodium channels open, sodium rushes into the cell. It is also important to note that at negative 55 millivolts, there are also potassium channels, voltage-gated potassium channels that start to open. However, this happens very, very slowly because these channels open significantly slower than these sodium channels here. Of note, potassium is no longer quite as motivated to stay inside of the cell because since all of the sodium is coming inside, the inside of the cell is no longer as negative as it used to be. And potassium is chemically motivated to leave to begin with. So it starts to leave, but very, very slowly. This actually does not become really applicable to a little bit later, and we'll talk about that. So as mentioned, as the sodium comes in, the positive charge causes the membrane potential to rise and rise and rise until we reach about positive 40 millivolts. At this stage, we don't really get much higher in our membrane potential, at least not as high as negative 62 millivolts or the happy place of sodium. This happens for a couple of reasons. First of all, these potassium channels, which we just talked about as opening very slowly, at this stage they're just about open. So because of that, potassium then will start to leave. So because positive charge is leaving, we cannot really get too much higher in membrane potential. Additionally, these voltage-gated sodium channels actually have a ball and chain mechanism. That is because during this depolarization stage, hydrophobic residues gradually become more exposed in the channel protein. And this ball, which is on the channel protein, also has hydrophobic residues, which becomes attracted to these hydrophobic residues, which are exposed during depolarization, and wants to interact with those residues. And it actually plugs the hole, so to say, of the channel. So sodium is no longer allowed to come inside. So because potassium has started to leave and because sodium is no longer allowed inside of the cell, we actually start to see a decrease in membrane potential and it becomes more negative. During this time, another action potential cannot be fired until we reach threshold because these voltage-gated sodium channels are closed, so there is no possibility of another action potential being fired. So this is known as the absolute refractory period. When we get back to negative 55 millivolts, the ball in the voltage-gated sodium channels falls out and we return to this stage once again. Potassium channels close very slowly, just like they open very slowly as we just talked about. So even though they're starting to close, potassium is still leaving as they are closing. So we actually dip below this negative 65 millivolt range, and we can actually get down to negative 85 millivolts. This is known as hyperpolarization because we are becoming more negative. Another action potential technically could be fired during this stage, but a much stronger stimulus would be required. During repolarization, the resting membrane potential is restored with the sodium-potassium pump that we talked about in the last video. So all of that extra sodium is kicked back out, sodium is kicked back out and potassium is allowed back in. So then we get back to negative 65 millivolts. So it's actually the concentration gradient of sodium that allows us to move along the axon with the action potentials and for those action potentials to move along like dominoes. So it is not like there's one action potential going across the entire neuron, but any portion of the neuron could be at some point of the action potential. Minimal leakage is what keeps us above threshold so that we can maintain an action potential. If sodium was allowed to leak out through leak channels along this axon, we would lose, we would no longer be able to fire action potentials as the positive charge would be leaving. So myelin is largely responsible for this, so that ions are forced to move down the cell. Action potentials are propagated in the breaks of the myelin sheath, known as the nodes of Ranvier. These breaks are necessary so that we can add more sodium for the next action potential. Thank you for watching this video.